This is the last part, part 7 of week 1, composition of functions. So we already talked about arithmetic operations with functions, addition, multiplication, and division, but this here is something different, which we can do with two functions. So let's say we have two functions, f and g, and let's say f is defined on domain x and the codomain is y, and g is defined on domain y, which is simultaneously the codomain of f. And the codomain of g is, say, the entire real line. So graphically, we have x, we have y, and we have the real line. And f maps elements of capital X to capital Y. And g maps elements of capital Y to the set of real numbers. We can now define a third function called the composition of g and f. Composition g and f. We write this using a special symbol, g little circle f, and the way it's defined is very simple. G composition f applied to some x is simply g applied to the image of x under f. That is for every x in the set capital X. Now there are some comments here for us to make. Well, first of all, of course, this only makes sense when g is defined on the image of f. That's the first comment. So the composition g composed with f g composed with f only makes sense when the image of f, the image of the internal function, is a subset of the domain of the external function, g. Image of the internal function has to be a subset of the domain of the internal function. The other comment here that I want to make is that we need not confuse the composition and product. G composed with f is not the same as g times f. In particular, the product of function is of course commutative, meaning that g times f is of course the same as f times g. but the composition is not commutative. G composed with F is in general not the same as F composed with G. And the next example will show a situation of exactly this, when G composed with F and F composed with G are different. So the example is this. Let F be square root of x minus 1. So in particular, that means the domain of F is all those x's that are real numbers for which x minus 1 is greater or equal than 0. The expression under the square root has to be non-negative, which of course is the interval 1 infinity. And let g of x be the function 1 over x squared. The domain of g is the entire real line minus 0, which is the union of open intervals negative infinity 0 and 0 positive infinity. So let us see if we can compose f with g and g with f. Right? So when we think about the composition f composed with g, right, when thinking of the composition f composed with g, we want x in the domain of g such that the image of x under the action of g, g of x, be in the domain of f. Because remember, f composed with g is f of g of x. In order for this to make sense, g of x has to be in the domain of f. And again, domain of f is the interval 1 positive infinity. In other words, we want x in the domain of g, so x is non-zero, such that g of x, which is 1 over x squared, be in the interval 1 infinity, which is domain of f. This simply means that 1 over x squared is greater or equal than 1. This inequality is equivalent to x squared is less or equal than 1 and greater or equal and strictly greater than 0. This simply means that x is not 0. Right? X squared is always non-negative, and saying that x squared is strictly positive simply means that x is non-zero. This is logically equivalent to x being in the interval negative 1, 0, union 0, 1. Or you can say that this is negative 1, 1, including the endpoints minus the set containing 0. Now, for such x's, right, for any x in this set, we can find f composed with g of x. which is f of g of x. Again, g of x is 1 over x squared, f is root of x minus 1, and when we compute f at 1 over x squared, we get square root of 1 over x squared minus 1. Again, x is from negative 1 to 1, except 0. Now, let's compose g with f. So do the same process in the opposite order. For the composition of g with f, right, we look for x in the domain of f, right? We want to determine the domain of g composed with f, so we look for all those x's in the domain of f, which is the interval 1 infinity, for which f of x, which is square root of x minus 1, lies in the domain of g, which is, again, negative infinity 0, union 0, infinity. Specifically, we want IE, right? We need all those x greater or equal than 1, that's the domain of the function f, for which f of x, which is root x minus 1, is not 0. So we need everything greater or equal than 1 except 1. Right? The domain of g composed with f is the interval 1 to infinity. And when we compute g composed with f, right, that's g of f of x, and f of x is root x minus 1, and g is the square reciprocal function, root 1 over argument squared. Now this time I don't need the absolute value, right? Square root of x squared is absolute value of x. But when you square the square root of x, it's simply x because x here is always non-negative. I mean, you can write absolute value of x, but that's always x because x here must be non-negative. It's under the square root. So I end up with 1 over x minus 1. Here x equals 1 infinity. X is in 1 infinity. In particular, it's very important to note here that f composed with g and g composed with f are two different functions. They have different graphs. In fact, it's easy to draw the graphs. Let me show them to you. The graph of f composed with g. All right, so it's root of 1 over x squared minus 1. So it'll look like this. You can use Desmos to make a picture of it. that is f composed with g of x, root of 1 over x squared minus 1. Now the graph of g composed with f. G composed with f is 1 over x minus 1, and that has a picture like this. In particular, it's very clear in the graphs that f composed with g is not the same as g composed with f. Also, there's another comment to make here. It would be incorrect to say that g composed with f is simply 1 over x minus 1, because the graph of 1 over x minus 1 doesn't look like this. It will have the other part when x is less than 1. It will have the other branch. So it's important to keep in mind that when you compose functions, keeping track of what your domain is very important. It would be incorrect to say that g composed with f is the same function as 1 over x minus 1, because if you draw the graph of 1 over x minus 1, it will look different than the graph of g composed with f. Compare this graph and this graph. They are indeed different. The graph of g composed with f is only one branch of that hyperbola. 1 over x minus 1 is a hyperbola consisting of two branches, and the graph of g composed with f is only one branch. The graph of 1 over x minus 1 is a hyperbola consisting of two branches, whereas the graph of g composed with f is only one branch. Of that hyperbola. So these are different functions. You absolutely have to identify the domain here. The domain is 1 infinity, and the domain here is real numbers except 0. Not true. I apologize. Not true. And the graph is incorrect. Let me draw it more precisely. The domain is the interval negative 1, 1 except 0. And the graph actually only between negative 1 and 1. Which again makes it very clear that f composed with g and g composed with f are very different functions. All right, and maybe one more example, computing compositions of functions given by a table. So use the table to compute f composed with g of 1 and g composed with f of 4. The table is this: x, f of x, g of x. Values of x are 1, 2, 3, 4. Values of f are 6, 8, 3, and 1. Values of g are 3, 5, 2, and 7. We can easily find that f composed with g of 1 simply is f of g of 1. G of 1 is 3, so I need to evaluate f at 3, and f at 3 is 3. And likewise, g composed with f at 4 is simply g at f at 4, and f at 4 is 1, so I need to evaluate g at 1, and g at 1 is 3. Note that particular values could be equal. It doesn't mean that the fact that f at g at 1 and g at f at 4 are the same number doesn't, of course, mean that they're equal functions. They are equal at different values of the argument. There's another example like this for functions given by graphs, where you need to compute the values of their compositions. This example is in the PDF that comes with this video. This finishes week 1.